Yes folks, Hume again, how are you going? In this video we continue with our series where we delve into topics on the CSEC additional mathematics syllabus. This time we're going to be talking about radians. What is a radian? Right? What is the relationship between radian and degrees? But before we get to that, let me delve into our general discussion of angles and angle measurement. In our previous video, in one of my mathematics videos, I would have discussed the whole concept of an angle as being the space between two lines where the two lines meet, where they intersect at a point. So anytime you have two lines meeting or intersecting at a point, the space between them is called an angle. So that is an angle. This here is also an angle. Alright? But let us, for the sake of simplicity, ignore the extensions of the lines and just deal with them as actually meeting at a point. So that is an angle. So that is the space between two lines where they meet at a point. There are different ways of measuring angles, the most common of which is the degree. So we know, for example, that there are 90 degrees in a right angle. We know that there are 180 degrees in a triangle. We know that there are 360 degrees in a circle, 360 degrees in a quadrilateral, etc., etc., etc. But most people who don't go beyond a particular point in mathematics may not be aware that there are other ways of measuring angles. All right, so for example, we know that there are 90 degrees in a right angle, but the same right angle contains 100 gradients. Hi, look trouble now. And this same right angle contains 1.57 radians. So right here, we have three ways of measuring angles. We have the degree, which is familiar to everybody. We have now this degree is not to be confused with degrees Celsius, all right? Degrees Celsius is a measurement of temperature, not angles. Big difference. We use the same small zero, but when we measure in temperature, that small zero is normally accompanied by another letter. So you have 90 degrees Celsius versus 90 degrees Fahrenheit. Of course, even though you have the same number, the fact that the units are different should suggest that these two things are not at the same temperature. All right? Of course, we also have the unit of absolute temperature, but that's a separate discussion. That is physics. We're not even going into that here. All right? So you have radians, gradients, and degrees. So let me deal with these two first because we're coming to this guy here. Generally speaking, as often as possible, anytime we have to discuss some concept or some entity, what I like to do is define the thing that we're talking about. In most cases, it is possible to define it in such a way that people understand what you're talking about. Sometimes the definition is so complex that you either give a shorthand version of it or you just ignore the definition of it. You just ignore the definition altogether, sorry. So you just go with it. All right? So for example, we define a circle. Now, most people who are not doing maths at a particular level, if you ask them to define a circle, they'll be lost for words, literally. But if you ask them, if you have a lineup of shapes on the wall and you ask them to show you which one is the circle, they know what a circle is. So we don't want to get too caught up with the definitions, but I like to define just for the sake of exploring the understanding at a deeper level. All right? So the degree, yes, I went on Google to check this out too. The degree is generally, and hear how complicated this thing gets. The degree is generally defined as a measurement which is 1/360th of a revolution of a circle. Yeah, you see where we're going already? The gradient is defined as 1/400 of the revolution of a circle. Hence, you have, anyway, I'll come back to that just now. So in other words, you have 400 gradients in a circle. Alright? So the same way you have 360 degrees in a circle, 360 degrees, 400 gradients. And in terms of radians, you have what we refer to as 2 pi radians. We'll get to that in a little more detail a little later. Alright? So, in terms of these two, 360 degrees, we know that. Most people, some of whom might be able to do anything else with a circle, will tell you with absolute conviction that there are 360 degrees in a circle. And that is fine. Nothing wrong with that. Alright? So basically what we are saying is that a degree is defined as the angle subtended at the center by an arc on a circle that is 1 over 360 of the circumference. Right? 160 times 1 over 360, or 1/360th of the circumference. That is what will give you a degree at the center. So if this arc is 1 over 100 is 1, sorry. If this arc is 1 over 360 degrees, 1 over 360 of the entire circumference, then this angle is 1 degree. So what it means is that if the circumference of your circle, let us say for the sake of argument that the circumference of a circle is 360 meters. Let me use the unit of length. And you have an arc of length 1 meter on the circumference of that same circle. Then the angle subtended by an arc of length 1 meter on a circle whose circumference is 360 meters, that angle is 1 degree. Alright? If you take another circle, let me change the circle now. And if instead of 360 you make the circumference 400 meters, and again, you have the same 1 meter distance. Remember, it's a different circle, right? I just use the same circle here just for the sake of space and discussion. Same circle, right? But 400 meters is the new circumference. Then if you have an arc of length 1 meter here, the length of the arc is 1 meter, then the angle subtended at the center is the same. Well, it won't be the same. It will be 1 gradient. Right? That is to say that you have 400 of these things in the whole circle. Hence, for the right angle, which is quarter of the circle, you'll have 100 gradients. With the degrees is the same idea. With the degrees, if the circumference of the circle is 360 meters, and you have an arc of length 1 meter on the circumference of the circle, then the space subtended by that arc at the center is 1 degree. Which is to say then that you will have 360 of these things over the space of the whole revolution of the circle. So that a quarter of that will be 360 divided by 4, which is 90 degrees. Now, using this same idea, right, and I found it very interesting that in both cases, degree and the gradient, the angle was defined with reference to the circle, which makes a lot of sense because that is how we will define a radian. So using this same concept of defining 1 degree as the space subtended by an arc of length 1 meter on a circle of circumference 360 meters, and defining 1 gradient as the space subtended by an arc of 1 meter on a circle of circumference 400 meters. Using that same idea, using that same philosophy, using that same concept, it allows us now to arrive at a place where we could define the radian. Right? And in doing that, and when we come over here, you'll start to get a sense of the absolute stability of the radian. The radian is very stable. It is the most stable measure of angular space. Right? These things are kind of arbitrary, right? Because when you get into this, the first question you'll want to ask is, where did 360 come from? Why it wasn't defined as the space subtended by an arc of 1 meter on a circle whose radius is, let me say, 275 meters or 15 meters. 360, right? Now, that now is where you start to go back into the history of mathematics. And you start to examine where this 360 comes from and where they started using it. And it's how to make the connection to the number 60, etc., etc., etc. That is a discussion that we will not have in this video. But if you're curious enough, I suggest you check it out. Check it out on YouTube, check it out on Google. You have avenues now that were not available to me back when I was in school in the 90s. But that is the whole idea of civilization, of history of humanity. We evolve, we grow, we develop. All right? So you have all the means to get the information now. Go and stroke your curiosity. Find out where this 360 degrees come from. Same thing with the 400 in the case of the radian. Right? Not the radian, sorry. The gradient. So in the case of the gradient, the circumference was 400 meters. All right? Arbitrary, arbitrary. This one is even more arbitrary than this one, because this 360 would have come out of certain observations and experiences that certain civilizations would have had way back whenever. This 400 is a little more arbitrary than this 360, but we wouldn't get into that now. The radian, however, there is absolutely no arbitrariness that we can ascribe to the radian. And the reason for that is because the radian is defined in terms of the ratio of same arc on the circle, but you now, instead of choosing some arbitrary fraction, 1 over 360, 1 over 400, right? You choose some arbitrary measure for the circumference. In the definition of the radian, it doesn't matter what the circumference is. In other words, the radian takes the circumference totally out of the equation. All right, so in other words, over here, you needed a circumference of 360 meters to get a clear idea of what 1 degree is, if you have a 1 meter measure on the arc of the arc. In the case of the gradient, you need a circle of circumference 400 meters to get a clear sense of what 1 degree is. Sorry, what 1 gradient is, using a 1 meter measurement on the circumference of that circle. With the radian, however, the circumference is not a factor. The circumference doesn't enter the picture at all. And by taking the circumference out, you remove the arbitrary nature of the definition. And you now define the angle in terms, strictly in terms of the length of the arc and the radius, both of which are inherent properties of any circle. So it doesn't matter what circle you choose, what circumference the circle has. What circumference the circle has. It has a circumference and it has a radius. And remember that the whole concept of pi is the ratio of the circumference to the diameter. So the circumference divided by the diameter is what we refer to as pi. That is a constant. So there is a certain level of constancy, if I could coin that particular word. There is a certain level of inherent stability in this circle. And that is what we use to define the radian. So in other words, regardless of what the circumference is, if we make this arc here equal to, right, not 1 meter, right? So in other words, we don't need to measure any particular length now. If we make this arc equal to the length of the radius, so the length of this arc is r, this here is a radius as well, alright? So that is a radius, and that is a radius. So in other words, if we make the defining arc, the arc that we're going to use to define the angular measurement, if we make that equal to 1 radius, then the angle subtended by this arc at the center is equal to 1 radian. So the radian is all about the radius. The very definition of the radian springs from the existence of the radius. Radius to radius, right? Radius on the arc divided by radius at this radius from the circumference to the center. That ratio will give you your measurement in radians. So if this measure is 1 radian, so in other words, we now define the length at the arc in terms of the radius, in terms of the radius, and not as 1 meter or 2 meters or whatever. So over here, we made life simple by using 1 meter in both cases. In this case, it was 1 meter over 360 meters. That gives you 1 degree at the center. Over here, it was 1 meter over 400 meters, which will give you 1 gradient at the center, right? In both cases, the denominator was the measurement of the circumference. Over here, we take the circumference out of the picture and we talk about the measurement of the arc being equal to the length of the radius. That way, we don't need to say 1 meter here. All we need to do is make sure that this arc is equal to the length of the radius. We do that, and then boom, you have a radian in the center. And you come here and you make another r, boom, you have 2 radians at the center. You come here and you make another r, boom, you have 3 radians, and you have a little thing left off here. That's a pi that we'll come to a little later. And you go all the way around the circle, you'll end up with 6 of these with a little bit, 0.28, and that's what will give you 2 pi, which we'll come to a little later. But for now, we're just talking about the definition. So the radian is defined as the angle subtended at the center by an arc of length equal to the radius of the circle. Right? Let me say that again. 1 radian is defined as the angle subtended at the center of the circle by an arc on the circumference whose length is equal to the radius of the circle. So the radian as an angle measurement is essentially a ratio. As a ratio, it doesn't depend on any particular circumference relative to any particular measurement on the circumference itself. Right? Any circle you could think of, just make the arc equal to the length of the radius, and there is a radian inside there. And because of that, you find that there are a host of things that we could do with the radian that we will not be able to do with the degree or the gradient. Right? All of your calculus where trigonometry is concerned is done in radians, not degrees. So anytime in AdMaths you're dealing with trigs, AdMaths, pure maths, CAPE, whatever, once you get past a certain level and you're getting deeper into this whole thing of angles and stuff, trigonometry, so to speak, you will inherently find yourself working in radians, not degrees. And just as a general note, if you're using a calculator, you will almost invariably have to switch the mode from degree mode to radian mode. Alright? So that is something to always be aware of. Most of us, we use, because most of our maths up to a certain point is in degrees, you leave the calculator in degree mode. But then you reach a certain point, beyond which you must switch from degrees to radians. Then the calculator must also make the same switch from degrees into radians. Alright? So that is what a radian is. And even though on the CSEC Adma syllabus you're not required to define the radian, as I say all the time, anytime I am teaching something, I try as much as possible, whenever possible, to explain the things so that we can understand it. Yes, that will almost invariably mean taking a little more time, talking a little more, etc., etc. But what I don't want from my students, people who interact with me mathematically, is to just take stuff and run with it and you don't know what it is you're talking about. There will be times when you will have to just accept a definition without understanding it. And sometimes if you go further on into the mathematics, it is only as you go further on you really get to understand, well, oh, that is why so and so and so and so and so. If you don't go further on in your maths, you just leave it as it is. There will be times when you just have to take it. Go on faith, as we say. But I like to explain and define as much as possible. So, I don't know. I hope the extra talking doesn't cause too much stress. But I hope also, even more, that it would stimulate a certain level of engagement, a certain level of understanding, a certain level of curiosity. And that will make your mathematical journey a lot more enjoyable. And once it becomes more enjoyable, you're automatically on the road now to making it a little more easy. Of course, you still have to do some work and do hard work as well. Alright, so we have defined the radian. We established some of the core differences between the radian and the other two common degrees of angular measure, the degree and the gradient. Alright, now the next question we have to answer invariably is the question of the relationship between this radian, which we are saying as mathematicians is so critically important. We have to establish the relationship between the radian and the degree, which is the thing that we commonly use in most applications. So, prior to a particular point, almost everything you do will be in degrees. Your trigonometry will be in degrees, etc., etc., etc. But once you get past a certain point, you switch to radians, different kinds of applications. Alright? So invariably you want to get a sense of the relationship between degrees and radians. So let me do the thing. So we're going to rub off all of these guys here, clear some space on the board. We leave our radian circle up in the corner there, and we proceed as follows. So remember that your circumference is, scrap that. Remember that the angle at the sector, the angle of a sector at the center, and when I say angle of a sector, I mean the angle subtended at the center. Wait, before I say that, there's one thing I want to mention first. In fact, no, I'll come to that because that will come out of what we're going to talk about here. Alright? Remember, in your regular degrees, forget the radians for now. In your regular degrees, the ratio of this, for any sector of a circle, let me go general again. Yeah, don't mind the circle looking like a potato, small thing. Right? For any circle, the ratio of the arc length to the entire circumference is the same as the ratio of this angular measure here to all of the degrees in the circle. So in terms of degrees, for a semicircle, we know that this measure, which is half of the circumference, this measure over the whole circumference is the same thing as this angle over all of the angles. So we know with conviction that a semicircle is half the angles at the center, and a semicircle is also half of the circumference. So we start off with the fraction that we're most comfortable with, which is a half. And the same thing applies, let me say, for a quarter. So circle again. Right? Boom. We know that that's a quarter of a circle in degrees. It means then that this arc here, the length of this arc is 1/4 of the circumference, in the same way that the amount of degrees you have at the center is 1/4 of all of the degrees in the circle. So in other words, whatever the size of your arc, let me use a kind of arbitrary arc now, right? The length of your arc, let me call it S for the sake of remaining consistent to the ADMATS annotations, right? The way we write this thing. The length of the arc S, the ratio of the arc S over the circumference. In other words, S over C, where C is the circumference, that's capital C, that's common S, is the same thing as whatever your angle is here. Let me say angle over 360 degrees. Alright? So the angle subtended by the arc S, that angle over 360 degrees is the same thing as the same ratio as the arc itself, the length of the arc over the entire circumference of the circle. And if we take this idea and we bring it across here, then we start along the road of establishing the relationship between radians and degrees as follows. Let me switch up the colors a little bit now. Alright, so using this idea, we can say that since this here is 1 radian, right, then as a RAD short for radians, then the ratio of R, which is 1 radius length, to the entire circumference is the same as the ratio of 1 radian to your 360 degrees. So we immediately make a connection between the two. So in other words, R, which is the radius, over the circumference, big C, is the same thing as 1 radian over 360 degrees. Nice? We know, of course, that the circumference is 2 pi r. 2 by this constant pi by the radius itself. So, leaving this up for a little while. So we could say that r over 2 pi r is equal to 1 radian over 360 degrees. Alright? So we establishing a relationship between the radian and the degree using this formula. So we start to simplify. Alright? We cancel the r's. So if you have your r over 2 pi r being equal to 1 radian over 360 degrees, the r would cancel out over the r there, into the r there. So you'll have 1 over 2 pi being equal to 1 radian over 360 degrees. Alright? And here you could do one of two things. You could cross multiply, bring the 360 on this side and bring the 2 pi on this side, and you could say that 360 degrees is equal to 2 pi radians, or you could carry the 360 degrees alone by itself. which would then give you 360 over 2 pi. 360 degrees over 2 pi is equal to 1 radian, in which case 360 divided by 2 is 180 degrees over pi is equal to 1 radian, in which case 180 degrees cross multiply now is equal to pi radians. Alright? So this is how we get that 180 degrees is equal to pi radians. And that is important because we know that the number pi is 22 over 7. In other words, if the circumference is 22 meters, the diameter of the circle is 7 meters. Alright? Not that that is important strictly over here, but I'm just using that to make sure that we understand what pi is. Pi is 22 over 7, which is 3.14. So in other words, what we are saying is that 180 degrees is 3.14 radians, 3.142 radians. Let me write it up here just to make sure. Right? 180 degrees is 3.142 radians. Right? What that means in practice is that you have 1 radian there. Right? You come with the next r here, right? As 2 radians, 2r and next r. So this angle here is 2 radians. You come with our next r here. That's 3 radians. That's 3 radians here, and then of course you'll have a little thing left over, which would be a 0.142. So this would be 0.142 r. So in other words, the ratio of this little piece here to the radius would be 0.142. So you get 3.142 radians being equal to 180 degrees. And of course, you continue like that on this second half as well, and they get the same thing. 3.14 on this side, 3.14 on this side. That's 2 pi. Look at right here. 360 degrees is equal to 2 pi radians. 180 degrees is equal to pi radians. Both of these, two sides of the same coin. We're basically saying the same thing in slightly different words. So once we establish that, and we get a sense of where this comes from, then the next step is to get into some common values where we know, well, how many of the radians is equal to how many of the degrees. So we're going to rub off all of this now and give a little expose, so to speak. We go a little further in terms of getting some values where the relationship between these two angular measures is concerned. So we know from our previous work right here that (180 degrees is equal to pi. Sorry, let me start with the 360. Just for the sake of absolute completeness. Alright? We know that 360 degrees is equal to 2 pi radians. Alright? You divide that by 2, you get 180 degrees is equal to pi radians, which we also got in the course of our working. We were able to get these two relationships separately of each other. Of course, we realize that this is just 2 times this. Alright? Or we could say that this is half of this. And you just continue dividing as you go along. So you divide this 180 by, let me say, 2. So we know that 90 degrees is equal to pi over 2 radians. You divide the 180 by, let me say we divide this 90 by 2. Pi over 2 divided by 2 is pi over 4. So if we divide 180 by 4, we get 45 degrees is equal to pi over 4 radians. Right? And if we divide by 2, we could divide by 3. These are the two common values. So 180 divided by 3 would be 60 degrees. So let me say, all right, let me go in order. So we divide 180 by 2 and we get 90. All right? So 90 degrees is pi over 2 radians. 2, 3. If we divide 180 by 3, we get 60 degrees is pi on 3 radians, right? 180 divided by 3 is 60. Pi divided by 3 is pi over 3. 2, 3, 4. We divide 180 by 4, right? 45 degrees is pi over 4 radians. We divide 180 by 5. That will be 36. 36 degrees is equal to pi over 5 radians. We divide 180 by 6. We divide 180 by 6. 180 divided by 6 is 30. 30 degrees is equal to pi on 6 radians. 5, 6, 7, no, 7 wouldn't work. 8 wouldn't work. 8 could work, boy? No, if we divide by 4, we have 45. If we divide by 8, we get 22.5. Let me stick to integers for now. 9. We divide 180 by 9. So that 180 divided by 9 is 20 degrees. That is equal to pi over 9 radians. We divide 180 by 10. 180 divided by 10 is 18 degrees is equal to pi over 10 radians. We divide 180 by 10, 11, 12. We divide 180 by 12, you get 15. Right? 15? Oh, no. 180 divided by 12 is equal to, yes, 15. Right? So 180 divided by 12 is 15 degrees. 15 degrees is pi over 12 radians. 12, 13, 14, 15. And divide by 15. 180 divided by 15 is 12 degrees is equal to pi on 15 radians. Right? Divide by 12. 13, 14, 15, 16, 17, 18. You divide 180 by 18. Right? So we're going to rub off this circle here now. I don't think we need it right now. Right? So what I'm going to do is go back on top with these guys so that we can get as much of these things in as possible. Alright? So we divide 180 by, here's 180 by 6, 7, 8, 9. We divide 180 by 9. 180 by 9 is 20 degrees. So 20 degrees is equal to pi over 9 radians. We divide by 10. 18 degrees is equal to pi over 10 radians. We divide by 12. 15 degrees is equal to pi on 12 radians. We divide by 15. 12 degrees is equal to pi on 15 radians. We divide by 15, 16, 17, 18. We divide by 18. 10 degrees is equal to pi on 18 radians. We could go even further. We could divide by 18. Can we divide by 27? 180 divided by 27 is equal to, no. We could, but we stick into integers. 180 divided by 24 is equal to, no. So we divide by 18. We divide by 18 and we get this. We divide by 20 and we get 9 degrees is equal to pi on 20 radians. We divide by 20. 20, we divide by 30. 180 divided by 30 is 6 degrees. 6 degrees is equal to pi on 30 radians. 30, 40, we divide by 40. 180 divided by 40 is not 40, 50, 60. We divide by 60 and we get 3 degrees. 3 degrees is equal to pi on 60 radians. If we divide by 45, we get pi on 40. If we divide by 4, if we divide by 45, we get, well, I'll get the point, right? I'll get the point. So we reached as far as this. I really would like to continue, but in fact, I will continue just for the sake of argument on this other side. So you understand where we're going with this. Now, for the sake of CSEC, there are certain ones that you need to know for sure. This for sure you need to know. That for sure you need to know. That for sure you need to know. That for sure you need to know. Alright? So you need to know that pi over 2 is 90 degrees. You need to know that pi over 3 radians is 60 degrees. You need to know that pi over 4 radians is 45 degrees. You need to know that pi over 6 radians is 30 degrees. All of this is just me having fun. This is not absolutely necessary, but I went through the stress of doing it just to demonstrate that we could go as far as we care to go. However, for the sake of the syllabus, for the sake of the exams, make sure and know these. So in other words, I take you through the process so that you can understand where we get this 60 degrees is pi over 3 radians from. Right? So that you understand where we get this 45 degrees is pi over 4 radians from. So that you can understand where we get this 30 degrees is pi over 6 radians from. So that you understand where we get this 90 degrees is pi over 2 radians from. Once you understand the process, the memorization becomes easier. And in the event that for some reason your memory fails, then if you're aware of the process, you could fall back on the process and derive the result. That is the idea. That is what I try to bring across as much as possible when I am teaching the people maths. Yes, it's a little more work for me because it means that I don't get the option of taking the easy way out and just slapping it with formulas and saying memorize that. No, I ain't going through that. It also means too that it's a little more work for you, the student, to listen to me droning on and on and on for 45 minutes on one little topic that a lot of other teachers will probably just drop the formula and I'm done with that. 15 minutes and I'm ready to do past papers. Right? So I hope that you would have enjoyed. I mean, yes, sometimes it's kind of long, and yes, I understand that it's a little boring sometimes too, but that's alright. Right? One thing you will not be able to say with me is that I didn't go the extra mile, that I didn't go beyond, above and beyond to do everything that I could do to explain the topic, which is exactly why I have to record these things, because it's a lot of work for me to go through this once, for me to do this repeatedly. So when students come and they tell me, I don't understand how 90 degrees is pi over 2 radians, I send them right back here in this video. Alright, so don't worry about these. These are not really necessary to know. What you need to know is how we get that. And we get that by simply taking factors of 180 degrees. You divide by 180, and whatever you divide 180 by, you divide the pi radians by, and you get your relationship. So you divide 180 by 2 to get 90, pi radians over 2 is pi over 2 radians. You divide 180 by 15 to get 12 degrees, pi radians over 15 is pi over 15 radians, etc., etc., etc. Again, just to re-emphasize, pi on 2, pi on 3, pi on 4, pi on 6. Alright? And if for some reason they squeeze in pi on 5 in an exam, because you would have gone through this, is not something that is a shock, because You know how to get these, so you will also know how to get this. And once you see the pi and 5, you know, well, all right, 180 divided by 5 is 360. All right, etc., etc., etc. So, or on the flip side, if for some reason you have to deal with 180 and 360, 180 and 36, once you realize that the relationship between these two is that 36 is 180 divided by 5, then you immediately know that 36 degrees is pi radians divided by 5. Anyhow we look at it, you could derive even the uncommon ones once you understand the process of how we get all of these things. And once you understand the process, you can memorize it better and derive it if your memory fails. So, enough talking, enough repetition. This is the end of this video. And now that we would have spent time talking about the radian, we will continue where we'll get into some of the other aspects of the ADMAT syllabus, and we get deeper and deeper into this whole matter of trigonometry. So as always, take care, keep good, come back for more, bring somebody else when they come in. Alright? Stay on board, let we do the thing, let we enjoy it, and let we do it nice. Boom.